Let's turn our attention to the feedwater heaters. In our earlier example, we looked at a system which contained 4 stages of feedwater heating. However, it is quite common to have 7 stages and even more. Moreover, in large plants, each stage may consist of 2 feedwater heaters. However, in all of this, the principle of operation is the same. So we will continue our discussion by looking at the 4 stages of extraction. There are 2 basic types of heat exchanger used in the feedwater system. That is, the closed type and open type. For example, the 2 low-pressure heaters shown here are of the closed type, meaning that the condensate passing through the heater does not come into contact with the extraction steam, which is providing the heat. Closed feedwater heaters may be constructed in the vertical position like this, or horizontally as shown here. In either case, the internal construction is similar. This type of heater is known as a tube and shell heater. Water enters at one side of the water box and passes through U-shaped tubes to exit at the other side of the water box. The condensate is pushed through the large number of tubes, typically about 300, by the pressure on the condensate pump discharge. The tubes are supported and held in place by internal baffles. Extraction steam enters the shell and fills the space around the tubes, consequently giving up heat to the water passing through the tubes. The steam condenses and falls to the bottom of the heater from where it is drained, passing through the heater drain system back to the condenser. As the steam condenses, it releases a small amount of dissolved gases such as oxygen and carbon dioxide. It is important that these uncondensable gases be removed, otherwise they will collect around the tubes and provide a resistance to the transfer of heat. The gases are drawn off through the vent system, which is piped back to the condenser. In practice, vents are fitted at both the top and intermediate level of the heater. The reason for this is that air finds its way to the top of the heater, while carbon dioxide remains at the lower level just above the water level. In most plants, the venting arrangements are as shown here. You can see that the upper and lower vents from the heater join together and pass through this orifice direct to the condenser, which is, of course, operating at much lower pressure. The objective of the orifice is to reduce the flow. Otherwise, excessive steam may pass through the vent in addition to air and carbon dioxide. However, during startup, the difference in pressure between the heater shell and the condenser is not very great. Therefore, in order to make sure that the heater is well vented, a bypass valve is fitted around this orifice. This valve should be opened during startup and closed when the unit is placed online at minimum load. In the example shown here, both low-pressure heaters are vented to the condenser. Now let's take a look at the heater drains. Remember that the B heater operates at a higher internal pressure than the A heater, and this in turn is at a higher pressure than the condenser. The heater drains are therefore cascaded like this. The drains from heater B pass into heater A, where more heat is given up. The combined drains from A heater pass into the condenser. Control valves are placed in both heater drain lines to maintain a minimum water level at the bottom of each heater. The operator must always note the position of these control valves as part of his regular inspection. As you would expect, at higher loads, more extraction steam is being condensed, and consequently the control valve must be opened quite wide in order to maintain the level inside the heater. If the control valve for some reason or other becomes defective and opens too far, then all of the water would drain from the heater and steam would blow straight through into the condenser. This would be extremely wasteful, as the steam is not condensing and giving up its latent heat to the condensate. Conversely, if the valve is defective and does not open enough, the water level will rise in the heater and blanket a number of tubes, so reducing the effectiveness of the heat exchange. One highly dangerous condition that can occur is internal tube leakage. In this situation, condensate could pass directly into the shell of the heater and rapidly fill the space inside. This water could then pass back up through the extraction line and into the turbine. As we have mentioned several times before, this is prevented by the positive closing non-return valves on the extraction lines, which close when high water levels occur in the heater. In some installations, the high water level causes the condensate to bypass the heater altogether by automatically operating the motor-actuated isolating valves in the following sequence. Open bypass valve and then close inlet and outlet valves. The matching of extraction steam flow to the heater and condensate flow through the heater takes care of itself automatically. As more condensate is pumped through the heater, more steam is condensed, so reducing pressure and pulling more steam from the turbine. In operating closed feedwater heaters, the operator must be sure to check that venting and drainage of the heater is functioning correctly. In the system shown here, we have another closed heater on the high-pressure feedwater side of the system. In this case, operation of the heater is similar to the LP heaters. The main difference is that the heat exchanger must be built more ruggedly to withstand the much higher pressures on both the feedwater side and the extraction steam side. As before, care must be taken with venting and drainage of condensate from the shell. However, in the case of this high-pressure heater, both the vent and heater drains are piped to the de-aerator, which of course operates at lower pressure. In many plants, this differential is insufficient at low load to create the flow of drains from heater to the de-aerator. Remember that in many plants, the de-aerator is located at a high elevation. To avoid this problem, the high-pressure heater drain can be alternatively routed to the condenser by automatic operation of control valves. Okay, now let's turn our attention to the